So we left off last week with a discussion of nearest neighbors. And we said the general idea was that you store some training data. Then when you have to classify a new point, you search through the training data and find the nearest neighbors using some distance metric of your choice. Then if you're doing classification, you can predict the most frequently occurring classes among the nearest neighbors. If you're doing regression, you can predict the mean value of the nearest neighbors. And we said it has some strong advantages. The result is very interpretable. It's easy to point to the neighbors and say, oh, we chose this particular class because this sample is very similar to these other samples. And it generally works well in low dimensions if you have a very complex decision surface. So it's capable of learning an arbitrarily complicated decision surface or regression line without having to have a fixed basis function that you know about in advance. On the other hand, the disadvantage is it's very, very slow, especially if you have a large number of training samples. The inference time increases in proportion to the number of training samples, actually in proportion to the number of dimensions times the number of training samples. So it gets very, very, very slow as you add more training samples. Now, this leads us to our next idea. So now we'll think about whether we can design a machine learning model that is also capable of learning very complex decision surfaces or regression lines without requiring a fixed basis function, but that's not so slow, so that the inference does not increase with n. So that brings us to today's lesson on decision trees. Decision trees are also a non-parametric method. So we don't have a fixed number of parameters to learn that we know about in advance. And like nearest neighbors, they can learn very complicated decision surfaces or regression lines. But unlike nearest neighbors, they could be much faster, especially in the inference phase. So let's take a look at these. Okay, so we had two models for regression so far. We had linear regression, and we had k-nearest neighbors. And we said with a linear regression, you could learn a linear function, or you can learn something that's in the shape of a linear basis function that you know about in advance. And with k-nearest neighbors, we said we can learn an arbitrarily complicated function shape. And then we had two models for classification. We had the logistic regression, where you said we can learn a linear decision boundary, or we can learn some, a linear basis function version of that we know in advance in order to learn a nonlinear decision boundary. And then we said we also have k-nearest neighbors regression, where you can learn an arbitrarily complicated regression line. So that was very flexible, but the prediction is extremely slow. So our next topic, we'll talk about a method that offers flexible decisions. It's a non-parametric approach, but with very fast prediction. So the decision trees, let's start with some tree terminology. I'm going to draw a tree. This tree is at the very top of the entire thing, so it's going to be called a parent. It's going to be called the root node. Now, it's also a parent because it's going to branch. I'm going to draw a couple of branches. And now this node has two child nodes. So it's a parent of node. Let's give them labels. A, B. So A is a parent of node B and node C. Okay. And B and C are children of node A. And let's draw a couple more nodes. Put that there for later. Okay, so a few more nodes. These nodes at the very bottom are known as leaf nodes. So I have 4 leaf nodes at the bottom that don't have any children. And we can also refer to the depth of a tree. So the entire depth of this tree from root to leaf is 2. Okay. So now we have some common terminology for talking about trees. Also, this particular tree is a binary tree, which means that every parent has 2 children, if it has children, unless it's a leaf node. More generally, you could have any number of children, but this particular tree has only 2 children per node because it's a binary tree. Okay, so that's some basic terminology. And in terms of notation, so we're going to follow a little bit different notation here because we want to be able to talk about features more easily. So when we want to talk about a feature, we're going to use a capital X notation. And when we want to talk about a sample, we're going to use a lowercase x notation. So this is a little bit different than what we have done before. Okay, so what's the idea of a decision tree? Well, imagine we have a set of possible predictors. So suppose we have 2 possible predictors, x1 and x2. Okay, and remember, we're using the notation where capital X means it's a feature. So we have this feature space defined by x1 and x2. I'm choosing 2 features because it's very easy to draw 2 dimensions. The idea of a decision tree is that in training, we divide the entire feature space into non-overlapping regions by splitting on 1 feature at a time. What does that mean? Well, maybe the first split, I'm going to say, okay, first I'm going to split on, say, whether x1 is greater than or less than a. Okay. Now I have 1 region to the right and 1 region to the left. So now I have 2 regions. Then I'm going to split again. Okay. And I'm going to draw the tree as I do this. Okay. So first I said I'm going to split on whether x1 is greater than a. And then I have a yes branch and a no branch. So let's say in the no branch, so which is the no branch? It's this region on this side where x1 is not greater than a. So on the no side of the tree, I'm going to split again. And maybe this time I'll split on x2. Okay. So in the no branch, I'm going to split on whether or not x2 is greater than some value b. And then I have 2 regions. So this region at the top is the region where x1 is not greater than a, but x2 is greater than b. Let's color that region in 1 color. Okay, let's call this the orange region. So this particular leaf node of the tree corresponds to this orange region up here. It's a region where x1 is less than a, but x2 is greater than b. Then similarly, we could define this region where x1 is less than a, but x2 is less than b. Let's make this, I'll make it a pink region. And then maybe we'll split some more on the other side. Maybe I'll split on x1 again. I could split on a feature more than once. So maybe this time I'll split on whether x1 is greater than c. Okay, so I have another split here. And I have a yes side and a no side. Okay, and then let's make the yes branch purple and the no branch blue. So you can see I've split up this feature space using my tree. So every time the tree branches, the feature space is split up more and more. Now, how does that help? Well, remember, we're doing some sort of classification or regression here. Okay, so now imagine we have some points here. We can imagine this is let's imagine it's a multi-class classification problem. Okay. And let's say we did a very good job, actually. So suppose we have the following points and we have 4 classes. Okay, so we have 4 classes. And let's say this is our training data, where each color represents a different class. So now suppose we have a new test sample to classify. Let's say there's a black sample here. We'll take this black sample and we'll look at the feature values along the X1 and X2 axis. So we'll say, okay, is the X1 value of this sample greater than A? Yes, it is. Okay, we'll take this branch. Then we'll say, is the X1 value of this branch greater than C? No, it's not. All right, we take this branch. And we land up in this blue region. And then our prediction will be based on the training samples that are also in this region. So in this case, all of the training samples in the blue region are blue. So we're going to predict blue for our test point. What if we had a few other color training samples mixed into the blue region? Well, that's okay. We're just going to predict the mode of the training samples in the eventual region as a prediction for a new point. So in this region, the most common class of points in the region is blue. So I'm going to predict blue for the new test point. If we were doing regression, we might instead use the mean of the labels of training points in that region. But the general idea is the same in either case. So you divide your predictor space into a bunch of non-overlapping regions by splitting sequentially on one feature at a time. And then for each observation that falls in a particular region, your prediction is either the mean of the labels of the training points in that region or the mode of their labels. Okay. So this is a general idea behind a decision tree. And we showed it in terms of, let's say, regions of the feature space, but you can also think about it directly using the tree. So directly using the tree, at every node that's not a leaf, you test one feature, and then you branch from that node depending on the value of that feature. And then for every leaf node, you predict y hat as the particular y hat for that region. So every region or every leaf node has some prediction that's kind of predefined by the training samples. So as soon as you know what region the test sample falls in, then you also know what the prediction is for that test sample. Okay, and we said we can characterize a tree by its depth, which is the max length from the root node to a leaf node. So this tree has depth 2. And we can also characterize by the tree by the size of the tree, which is the number of leaf nodes. And in this case, we have 4 leaf nodes. Okay, any questions about our decision tree so far? This is an illustration from one of the textbooks. So it shows a decision tree and the corresponding regions in a two-dimensional feature space. And the vertical axis here shows the same two-dimensional feature space, but with the prediction for each region. Right? So if, for example, this was a regression tree, you could see the value would predict in each region. The region on the image on this top left here, this is a type of stratification that could not be produced by a decision tree. Because in this case, you're not doing sequential splitting on one feature at a time. So you can't produce any possible stratification using the decision tree. So this type of kind of division is not possible. But if you keep branching and branching as many times as you want, you can ultimately produce a very complicated decision region or a very complicated regression surface. Okay, so how do we train a decision tree? So suppose I have these samples here, but obviously I don't have the regions. And this was our test sample. Okay, so I have these samples here. How should I go about training my decision tree? Okay. So we're trying to create divisions that classify well. Now, computationally speaking, there are ultimately many possible partitions, right? So how do we go about deciding how to partition the feature space? For example, for the first partition, you can potentially split on x1 over here. You can split on x1 over here, x1 over here, x1 over here. You can split on x2 in any of these potential positions. And then every decision you make will then affect your later decisions, right? So if you split on, okay, so let's say I decide that for my first split, I'm going to split at this particular position here for x2. Now that might be a valid choice. It might even be the best particular choice you could make at a particular instance. But this means that, let's say in a later situation, you're not going to be able to split the entire space like this. I mean, if you did that, it would have to be two separate splits like this and like this. So there are infinitely many possible splits to consider at every step. And not only that, ultimately the classification accuracy doesn't depend on the split that you choose at one specific step. It depends on the overall sequence. So there's even more potential sequences of potential splits. And in order to find a truly optimal solution, you would have to consider all of them. So that's computationally impossible. It's impossible to find an optimal tree. Instead, what we usually end up doing is kind of a top-down greedy approach. What is a greedy approach? It means that at every step, we make the decision that seems best according to, let's say, whatever metric we're trying to minimize at that stage. So for example, classification error at that stage, without looking ahead for what might yield a better result in some future step. Okay. So that means the first time I make a split, I'm going to consider many possible splits based purely on what is the result on this particular split. So when I evaluate all of these potential splits, The same goes for the x2 axis. I'm not going to think ahead to, let's say, what is this split in connection with this other potential future split? I'm only going to evaluate one split at a time. Okay, so that's a greedy decision. Then how do I evaluate a particular split? Okay, so let's say I want to consider splitting right here. Okay, so one option is classification error. I could compute, let's say, the result of a tree that splits right there. And then I can decide whether, I can, let's say, compute the classification error for this split, for any other possible split I might consider. And then I can choose a split that has the lowest classification error. Now, this is valid. You could potentially do that. But most often, we're not actually going to do that. Most often, we're going to choose a different metric. Okay. So what kind of metrics can we consider? Let's think for a moment about why classification error might not be the best choice. Okay. So suppose at this stage, I'm going to put some more blue points in here. Okay. So suppose at this stage, I'm considering this particular split that's shown here. And perhaps the true value in this region up here is purple. Okay. And the true value in this region down here is blue. But if I'm considering a split at this particular location, I'm not looking ahead to see what if I split here and then split here. I'm just looking to see what happens if I split here. So if I split here, what is the classification for this entire region on the right going to be? Okay, so the most common class on the right side of that point is blue. So the classification for this entire point is going to be blue. Okay. So our classification error might actually be pretty high because all of these points in the purple region will be misclassified. That's okay because I can, then split again in the future. So we want something that's going to behave a little bit differently than classification error. Now, the metric we're going to use actually has the same property. But the metric we're going to use is something that basically tries to group similar points together. Okay. What does that mean? It means we're looking to make splits so that we have similar points in the same region, and points that are not similar should be in different regions. And the type of metric we're going to use is called an impurity metric. Okay. So if you have a node where samples all belong to the same class, it's considered a pure node. If you have a node whose samples are evenly distributed among classes, it's considered very impure. So imagine we have a node where we have 2 orange, 2 red, 2 blue, and 2 purple. That's an impure node. And we're looking to split in order to produce the most pure nodes possible. Okay. How do we do that? Well, one possible way, as we said, is misclassification rate, but we don't use it very often. There are 2 other metrics of purity, or impurity, as you will, that often have better results. One of them is known as a Gini index. And this is the proportion of class samples in the region belonging to a particular class times 1 minus the proportion of the same proportion. And the other alternative metric of impurity that's often used is called entropy. Okay. And this also uses, let's say, the proportion of training samples in a region belonging to a class. So 3 possible metrics for deciding how to split at a particular stage. You have the misclassification error, that's the purple line here. You have the Gini index or the entropy. So you could see they all have the same kind of general behavior as the proportion of nodes belonging to a particular class varies. So this visualization shows these measures for a binary classification problem, where the proportion of nodes belonging to the positive class goes from 0 to 1. Okay, so we have 2 classes. And now suppose all examples belong to the negative class in a particular node. By all metrics of impurity, the impurity is 0 because they all belong to the same class, the negative class. So when the proportion of samples in the positive class is 0, the impurity is also 0. Now, suppose we start to gradually increase the proportion of samples in the positive class. Well, when 100% of samples are in the positive class, the impurity is again 0. When is the impurity highest? The impurity is highest when the node is 50-50 positive and negative samples. That's the most impure node you can possibly have. So this is a typical approach when splitting for classification. At each split, you measure the node impurity, and you choose the split among all your possible choices as the one that ends up with the smallest impurity. So we'll do an example in a moment with the entropy impurity metric. I just want to mention that if you're doing a regression tree, then at each split, you're going to look for the greatest possible reduction in squared error. So there you would, let's say, compute the squared error at the current node, right? So what do I mean by that? Okay, let's draw this actually. So suppose you have this regression tree. So I have a node here, and okay, so let's say this node is representing the entire feature space. So I'm going to kind of draw that representation next to it. And I might have many samples in the feature space. Okay, so this is kind of a regression problem where I have some gradually varying quantity. Okay. So if my entire tree is just a root node, that means I have no splits at all. Then my prediction for every sample is the mean of this region, which is the entire region. So I'm going to predict the squared error, meaning compute the squared error. Of this prediction, which is, just the mean of the entire space. Okay. Now, suppose I want to evaluate a split. So suppose I'm considering splitting like this. Okay, where maybe the split ends up like, okay, so maybe I'm splitting over here. Okay. So here I'm going to compute the squared error of the one region. Okay, so let's say I'm splitting on whether the value is greater than k. So I have greater than k. Let's say feature x1. So I'm evaluating whether I should split on x1 greater than k. I'm going to compute the squared error of prediction by mean of the left region. Okay. So if I split on k, then for any sample that falls in here, I'm going to predict the mean of this entire region. For any samples that fall on the other side, I'm going to predict whatever the mean is of the right region. Okay. So I'm going to compute 3 squared error values. Now I have 3 squared error values. We'll call them, let's say, L1, 2, and 3. So if I split on, let's say, x1 greater than k, then my new overall loss is going to be L2 plus L3. Okay, so my new overall loss will be the sum of the loss function at this node plus the sum of the loss function at that node. So in order to decide whether to split on x1 greater than k, I'm going to look at the difference between my old loss and my new loss. And I'm looking for the split that gives me the greatest reduction in squared error loss. So that's what I'll do for a regression tree. For a classification tree, we said we have these measures of impurity that I'll use at every split. So we're going to do example now using the entropy measure. Okay. And here's how it works. So when I split on some feature, I create, let's say, 2 subsets with different entropies. So just like in this example here. Okay, let's try a classification tree. So I split on a feature. I have entropy of the parent. And remember, entropy is an impurity metric. And then I have the entropy of the potential children. Okay. Now, we're going to compute something called the conditional entropy, which is the entropy of S, which is the entire set of samples, given that I split on, let's say, a particular X. So let's say the entropy of the entire set, given a split on feature X, is equal to the following. So I'm going to have subset 1 and subset 2. Okay. So I'm going to compute the size of subset 1 over the total set times the entropy of subset 1 plus the size of subset 2 over the total set times the entropy of subset 2. Okay. And this is known as a conditional entropy. And I'm going to choose the split that maximizes what's called information gain, which is the expected reduction in entropy gain due to splitting on X. So this is the entropy of the overall set of points in the parent minus the entropy of the resulting children, given that we would split on X. So let's look at an example that I think will make this clearer. Okay. So we have this data set, which we're going to use to decide whether or not I should play tennis. Okay. So we have these potential features: outlook, temperature, humidity, or wind. And our target variable is play tennis. It's a binary classification problem. either we play tennis or we don't. So I'm going to move this down here. So we're going to apply our entropy measure to this particular classification problem. At the very top node in my tree, this is the top node in the tree, all of the samples are in the top node. So I've represented each sample by their day number, and the color indicates whether it belongs to the positive class or the negative class. How many examples do I have in the positive class? How many examples do I have in the negative class? Okay, I have 9 positive samples, 5 negative samples, and that's a total of 14 samples. Okay, so the total size of the set is 14. Now I'll compute the entropy as follows. So the entropy of the entire set is minus 9 out of 14. Okay, so I'm going to compute minus 9 out of 14 log 2 of 9 out of 14 minus 5 out of 14 log 2, 5 out of 14. So this is the entropy of the parent. Now I need to evaluate possible splits. Okay, what are the possible splits? So here's my data here. Maybe I'll open this. Okay, so here's my data, a little easier to see this way. My possible splits are on outlook, on temperature, on humidity, or on wind. Okay. Let's suppose we want to evaluate the effect of splitting on wind. So I have 2 choices. I can split on weak wind or strong wind. Meaning I have 2 branches here. I have a weak wind branch and I have a strong wind branch. Which days will end up in the strong wind branch? Okay, so let's see, day 2, day 6, 7, 11, 12, and 14. Okay. So let's take day 2, put it in the strong wind branch, day 6, day 7, okay, day 11, 12, and 14. All end up in the strong wind branch. And the rest of the days end up in the weak wind branch. In the weak wind branch, I have 1, 3, 4, 5, 8, 9, 10, 13. Okay. Let's compute the entropy for each of these. Okay, so how many positive, negative, and total samples do I have in the strong wind branch now? We have 3 positive, 3 negative, and 6 total samples. So I'm going to compute minus 3 over 6 log 2 minus 3 over 6. Sorry, 3 over 6 minus 3 over 6 log 2, 3 over 6. So same computation there. Got it. And then on the other side, Okay, how many positive, negative, and total samples do I have here? See, I have 6 positive, 2 negative, 8 total. So I have 6 over 8 to 6. Now let's put some numbers on these. This is equal to 0.94. If you do some computations. This is equal to 0.8. And this one, I don't even need to do the computation. It's evenly split, so clearly there is maximum entropy there. Okay, so the entropy here is 1, right? So this is the entropy if I would split on wind. Okay. So at the top here, I have entropy S. Okay. And here I have entropy of S strong. Here I have entropy of S weak. And now I'll compute the following quantities. So I can now compute the entropy of S given a split on wind. Okay. Let's see. Is equal to some factor times entropy of S weak plus another factor times entropy of S wind strong. And I'm going to go in and put that factor in there. So the factor at the beginning is how many of the total samples get classified in the weak versus strong part. So I have 8 out of 14 in the weak branch and 6 out of 14 in the strong branch. So this quantity here is going to be the entropy of S given wind. Okay. And this will actually come out to 0.89. And now I'm going to compute the information gain. So the information gain of S, if I split on wind, is equal to the entropy of S minus the entropy of S given a split on wind. So 0.94 minus 0.89 equals 0.05. So this is the information gain if I split on wind. Now I have many other choices of things to split on. So in order to decide how to split, I need to do the same computation for every single one of them. I'm not going to go through that right now, but if you do that, let's see, you would find, okay, so this is the information gain of splitting on outlook. This is the information gain of splitting on humidity. This is the information gain of splitting on wind. And this is the information gain of splitting on temperature. And you would choose a split that has the greatest information gain. So at this point, you would split on outlook. Okay. You would split on outlook. Then after you split on outlook, you would go to each of the child nodes and start again there. Okay. So you would then consider all of the samples in the child node as entire set and consider possible splits. Okay, any questions on this process? Okay, one nice thing about the decision tree is it's very interpretable. So you can look here and see exactly why you ended up at this particular decision. Oh, there's a question. So one question is how expensive it is. Okay, so training time is, well, it depends. We said that finding an optimal tree would be basically extremely expensive because you have to consider infinitely many split points and look ahead many steps. So our greedy approach is obviously less expensive, but then it depends specifically on exactly how you do the training. There are many different decision tree training algorithms, and I don't know offhand what the exact runtime is of the most popular ones, but it's definitely much less than what an optimal tree would be. Now, one nice advantage of the decision tree is that the inference time is pretty fast. The inference time is in proportion to the depth of the tree. Okay. So you can see if you, let's say, have a new sample and you want to classify the new sample, you just have to follow the tree through every branch. So let's say if the tree is depth 2, you need to do 2 comparisons. So the inference time grows with the depth of the tree. Generally, if you let the decision tree grow until there is no impurity anymore, so until it exactly classifies every training sample, you'll have a very deep tree. So that will have longer inference time, but that's also disadvantageous for other reasons, which we'll get to in a moment. But the general answer is the inference time is much smaller than, let's say, the k nearest neighbors. Instead of, let's say, comparing to every possible neighbor, you only need to compare to every possible split. So it depends on the depth of the tree. Okay, that was a good question. Okay, so another advantage besides the runtime being, let's say, only an order of the tree depth, is that you also have a very interpretable result. So you know exactly why you made the decisions you made. And you can also get some measure of, let's say, feature importance. So if the feature was used very often for splitting, that tells you it's really useful for predicting the target variable. And you can get a measure of feature importance by, let's say, adding up the information due to split, adding up the information gain due to split at every node where that feature was used to split. And that's kind of a good estimate of how important that feature is, relatively speaking. Okay, I mentioned a moment ago that there are some good reasons not to let the tree grow as deep as it potentially can. So if you let the tree grow as deep as it wants, let's imagine this set here. Okay, so if we keep splitting and splitting and splitting and splitting, then we'll eventually classify every single point correctly. So we'll end up with something like this. I'm just drawing horizontal lines because they're easier for me to draw, but you get the idea. Okay, so you could ultimately end up with actually 0 error. Would that be desirable? So you could end up with a tree that has 0 training error by letting it grow very, very deep. But if you do that, you can see your learning decision regions that are very subject to the noise in the training data. Okay, so here, for example, you're going to learn these little regions as orange, all of these regions as purple, So you'll end up with very good training accuracy. But will your accuracy on a new data set be good? Let's say test error. So you would expect your test error to be high because instead of kind of fitting to the general trend, which is these regions shown here, you're actually fitting to noise in the data samples, in the training data sample, which, as we know, is exactly the definition of variance, when the tree depends very much on the particular draw of training samples, and it learns those particular training samples instead of learning the overall pattern. So if we let a tree go very deep, you'll have high variance. Just going to finish, say, drawing just some blue regions. Okay, so if you let the tree grow very deep, you'll have high variance. On the other hand, what if you restrict the depth of the tree and let's say limit it to a small number of splits? So what if I say, okay, I'm only going to allow one split? So if you only allow one split, let's say this entire split, well, then you end up increasing the bias of your estimate because you have some systematic difference between the true function and the estimate of your decision tree. So you can see that the depth of the tree controls this bias variance trade-off. If your tree is too deep, it's going to overfit to the training data and have high variance. If it's not deep enough, it's going to have high bias. So how do we control this? Well, one option is stopping criteria. So you can, if you build a tree until there's zero error on the training set, you'll overfit. So you could select in advance some stopping criteria like the maximum depth, the maximum size of the tree, the minimum number of samples in a particular node in order to be eligible to split it, the minimum number of samples that you can have after a split. You can specify a minimum decrease in loss function due to a split. So these are all stopping criteria that once you reach them, you stop splitting and it prevents overfitting. And you can then select these particular values by cross-validation. But you can see that that's kind of a lot to do. It's a lot of, let's say, heuristic decision-making and making model decisions that aren't necessarily best based on the data. Alternatively, you can do something called pruning. So the idea behind pruning is that you build the entire tree, and then you go ahead and unsplit some nodes. What do I mean? So let's say I have this entire tree, and I decide after the fact, you know what? It's actually not a good idea to split up the yellow and pink regions. Maybe these are actually all supposed to be like one common class. So I can build the entire tree, keep building the tree until I have memorized the entire training set. And then I'm going to look at all of the leaf nodes in my tree, and I'll think, okay, which ones can I merge to get the best improvement in performance? Now, the best improvement in performance, as we know, is not going to be training error. So let's say I would remove this split. So instead of splitting here, I'm just going to take all of the no samples and classify them into one common leaf node. Make this an orange leaf node. Is this tree going to have more or less training error than this tree here? So it's definitely going to have more training error. So how do I decide, let's say, whether to merge the two leaves on the right or the two leaves on the left? Well, I could do cross-validation, but if you end up doing that over every possible combination of pruning, that ends up being really expensive for cross-validation. Instead, I'm going to see, okay, so I'll compute the error of the overall tree. Let's call the overall tree tree 0. I'll compute the error of tree 0. And usually I compute the error of tree 0, let's say, using classification error and not impurity. Even if I, let's say, built the tree using impurity, let's say Gini index or entropy, for the pruning stage, I'll usually use classification error. Okay, so let's say this tree is tree 0. And this tree is T1. I have actually two possible candidates for tree 1. Let's draw them. Okay, I have this candidate, or I can merge these leaf nodes instead. And then I have this candidate. Okay, so let's call this tree 1A, candidate A, and let's call this tree 1B. So for every possible tree, okay, so I'm going to consider the error of tree 1A minus the error of tree 0. But I'm also going to consider the size of the trees. So I'm going to divide that by, let's say, the size of tree 0 minus the size of tree 1. Okay, so I'm going to compute this quantity. The error of tree 1A, oh, sorry, this is tree 1A. I'll compute the error of tree 1A minus the error of the original tree, which is down here. And then I'll divide that by the difference in size. And then I'll do the same thing for tree 1B. And then I will select, let T1 be the tree with the smaller of these. So I'm going to select T1 to minimize this quantity. So either tree 1B or tree 1A will become my new tree. Okay. Let's say tree 1A is the one that I decide minimizes this quantity. So let's say this quantity is less than this quantity. Then this becomes my new tree 1. And then I'll repeat the process. Okay, so this is tree 1. Then the next step will be to prune again. Okay, and now I'll have tree 2. Okay, so this is tree 2. And then finally, I might end up with tree 3. So I prune again, remove these child nodes by merging the samples into their parent. And now I have just tree 3. And then I stop because I can't possibly prune this again. Okay, so now I have a bunch of possible trees. Tree 0, tree 1, tree 2, tree 3. Okay, these are my candidate trees. And I know that obviously the deeper the tree, the more training accuracy I'll have. And obviously tree 3 will have the worst training accuracy. But remember, I'm not after training accuracy, I'm after generalization. So then I can use cross-validation to select the candidate tree that has best validation accuracy. Okay. So that's the general procedure of pruning. First, I let the tree grow as large as it wants to, basically grow the tree until there's no training error. Then I start to prune one pair of children at a time into their parent. And for each step, let's say I decide which child leaves to prune based on minimizing this quantity. And then I end up with a list of candidate trees. And then I use cross-validation to select the candidate tree with the best validation accuracy. Now, it turns out if you do this, it ends up being the same thing as what's called cost complexity pruning. And this example shows it, let's say, using the squared error loss function, but it's the same general idea. It ends up being the same exact thing as minimizing the loss function with a penalty for the tree size. Okay. And the strength of the penalty is controlled by alpha. So this is similar to the formulations you've seen for optimization for, let's say, a loss function with a regularization penalty, which makes a lot of sense. Here we know the tree size or the tree depth determines my bias and variance trade-off. So placing a penalty on the tree depth and optimizing with that penalty in place will reduce the variance by reducing the tree size. Sorry, this is the tree size, not the depth. Okay. So this pruning process actually ends up being the same thing as optimizing this expression, which is a loss function plus a penalty for the tree size. Okay, so that's what we've learned for decision trees so far. Now, what's good about them? Well, what's good about them is they're easy to interpret, close to human decision making. So humans make decisions in a similar way. They're also good because we can use them to derive feature importance. And they're also very good at handling mixed data types. We don't have to worry about normalization, different ranges, anything like that. And we can find interactions that linear classifiers cannot find. The disadvantage is, well, this bias variance trade-off is complicated. You need a deep tree in order to overcome bias, but then the deep tree has large variance. And they're also not very robust. So it's pretty easy to convince yourself that a small change in the training data can cause a large change in the overall tree. Why is that? Well, a small change in the training data, let's say if it affects what feature you use to split on at the root, you can see it will end up changing the entire tree. So trees in general tend to have high variance compared to other methods because a small change can cause a small change in the training data causes a large change in the estimated tree. So what can we do about that? Well, it turns out that trees actually lend themselves very well to a technique for reducing variance without adding bias. It sounds like magic, right? How can you reduce variance without adding bias? The answer is by combining many trees. That's it, okay. So we said a decision tree lets trees grow very deep, which have low bias and high variance. If you use some stopping criteria or pruning to prevent trees from growing deep, then you'll end up with low variance, high bias. Now, the idea of ensemble methods are that you can combine multiple learners, so trees or other type of models, where each one has high bias or high variance. So each one is high error. But you can create an ensemble of learners, let's say take their average prediction, in a way that gives you an overall better result. So you can combine learners with high variance in a way that reduces their variance. You can combine learners with high bias in a way that reduces their bias. So we'll talk about two types of ensemble methods. One type is averaging. In averaging, you build a bunch of base estimators and then average their predictions. And the combined estimator usually ends up being better than any single one because of reducing the variance. So let's take a look at our decision tree. if you would go ahead and train a decision tree on this data, let's say 100 times, are you going to get 100 different decision trees? Okay. If you train 100 decision trees on this data, you'll get 100 identical decision trees, assuming you're using the same, training algorithm for all of them. So if you train many trees on the same data, each one will be exactly the same. You're not going to get any benefit from averaging their output. You're just taking the average of many identical things. So we need a way to train many decision trees, but have them all be slightly different. Okay. The answer to this is called bagging. And the name comes from a technique called bootstrapping or bootstrap aggregation bagging. And the basic idea behind bootstrapping is you sample with replacement. Okay. So let's say I have this data set here. Okay, so this is my original data set. And I'm going to use it to create multiple, let's say, bootstrap data sets. By sampling with replacement. Let's get rid of this point. It's a test point. Okay. So let's say on one-time sampling, I might end up with, let's say, 0 copies of these particular points. But let's say 2 copies of these points. Now they're exactly the same point. I'm just overlapping so that you can see that they're, 2 copies of them. In another bootstrap data set, I might, let's say, not have this point, this point, this point, but instead I might have 2 copies of this point, and this point, and this point. And that's because I'm sampling with replacement. So the idea behind bagging is I create many bootstrap data sets. And in every bootstrap data set, it's sampling with replacement from the original data set. Then I train a tree on each bootstrap data set. Now, are my trees going to be identical? Okay, so these trees are going to be trained on slightly different data. So they won't be exactly identical. I'll have multiple trees, and then I'll average their result. Okay, so combine the outputs by either voting, if it's classification, or averaging. Voting means, let's say if I have 10 trees that vote for class 1 and 5 trees that predict class 0, then the combined output will be class 1. So this actually works pretty well. Now, there is one problem with this. So this works well to reduce variance, right? So I'm going to train many decision trees, let them grow as deep as they want. Each one individually will have high variance, but their average will have lower variance. The problem is that even though I want the trees to be, kind of different from one another, they end up being more similar than I want. Okay, so the trees end up growing very correlated. And you can imagine that if there is, let's say, a feature that's a very strong predictor, then most or all of the trees will split on that feature, even though they have slightly different data. So you end up with highly correlated trees, and you don't get the same benefit of reducing the variance. Okay. The solution to this is a technique called a random forest. The random forest is an extension of the bootstrap aggregation. Okay. So I'm still going to be considering many different versions of the data set. But now I'm going to consider only a subset of the predictors for each tree. So let's say for tree 1, I'm not allowed to split on x2. For tree 2, I'm not allowed to split on x1. So by, let's say, forcing each tree to only use a subset of potential predictors, I produce trees that are less correlated. So random forest is a combination of bagging, so using bootstrap aggregation, and split variable randomization, where I force each split to consider only a subset of the predictors. And this leads to less correlated trees than bagging alone. Okay. So that was one way of, let's say, improving overall performance by reducing variance. Another way is to improve the overall performance by, let's say, having many trees with high bias, but combining them in a way that reduces their bias. And this one actually, it's kind of difficult to understand just from the lecture materials, but I think it will become more clear on Thursday. So the idea here is we're going to iteratively build a succession of models, and each model will be very weak. So maybe an extremely shallow tree, maybe a tree with only one split. And we're going to use a technique where in each stage, so we're going to train it iteratively. So the bag trees were trained in parallel. They're independent of one another. Random forest trained in parallel. The boosted tree is trained iteratively. So one tree after the next, after the next. And in each stage, we're going to adjust weights so that every sample, the next tree will focus on the more difficult samples. What does that mean? Well, if in iteration 1, I made a mistake on samples 5 and 6, then in the next stage, in iteration 2, samples 5 and 6 will have higher weights, which means that they'll be more important in the error function, and the classifier is going to be more likely to focus on them and predict them correctly. Okay. So we'll compute in every stage a weighted error function and then weights for the next stage. Okay. And remember, in every stage, we're fitting kind of a shallow tree. And then at the end, we output the, let's say, weighted average of all the trees. So some of the trees are better than others. Okay. We're going to compute a weighted average of all the trees at the end, where the trees that happen to do better will contribute more to the final average. Okay, I'm not going to go through the details now because we're going to do it in our collab lecture. But let's just review the overall conclusions. So you can use a single estimator that has poor performance, like a very deep tree, which has high variance, or a very shallow tree, which has high bias. And then you can combine the output of those multiple estimates into a single prediction in a way that has better predictive accuracy. Now, the downside is that then it has less interpretability. With the original decision trees, it was very easy to look at the tree and understand why it made its decision. With an ensemble of trees, well, it's much more complicated because you might have 100 trees, each making a different decision, and then you're taking their average. Okay, I think that's all we're going to say about trees and ensemble methods. Are there any questions on that before we move on to our second topic? And I know I kind of glossed over the boosted tree, but we'll look at that much more closely on Thursday. Okay, so Michael asked, when combining multiple estimators, doesn't that increase the variance? So the answer is no, that taking the average of many things kind of smooths them, reduces the, let's say, effect of any individual sample any individual sample's contribution. So that decreases the variance. So you can think about it as kind of having a smoothing effect where it smooths out the noise of any individual sample's, let's say, overweighted contribution. The other ensemble method, aside from averaging, was called boosting. And we'll get into that in more detail on Thursday, but the idea behind boosting was you iteratively build trees with high bias, and then you take a weighted average of them all at the end for the prediction. Okay, any other questions? All right, let's